I had one less lecture because it was always Pi Day sitting in between the course. So I don't have a formalized material for today's lecture. I'm open to discuss whatever topics can be most interesting. If you want to start with some questions, that could be a good starting point. Otherwise, I can speak about the branes and supersymmetric string theories until sunset. So. Any questions about? Yeah?
So when you obtain in the superstring, when you obtain the graviton and the gravitino, can you also prove that they satisfy Einstein's equations?
So if you just show that the superstring, the string theory reduces to quantum theory at low energy, it's automatic. Because there are, again, these theorems that tell you that whenever you have a spin 3/2, whenever you have spin 2 field that is massless, it satisfies Einstein equations at the lowest order and couples to matter in the standard way. And whenever you have spin 3/2 field, which is massless, it is a gravitino and satisfies and has a supersymmetric couplings to the matter fields.
So these Einstein's equations, these Einstein's equations have higher order terms, but do they? Well, usually when we put higher order terms, at least in 3 or 4 dimensions, we lose unitarity.
You should be really careful in thinking about effective quantum theories.
Mm-hmm.
So if you have an effective quantum field theory, you add an arbitrary number of higher order terms. Okay. But they are always taught as expansions around some background, how do I say this? You cannot trust any solutions where the correction terms dominate over or the same order of the zeroth order term. It is an effective theory. All of these violations of unitarity and so on have to do, happen already at the classical level pretty much, like the superluminality or things like that. But they happen only for solutions which are not, for which these extra terms are important. So they're meaningless. So if you take any unitary quantum field theory, some degrees of freedom, and then you ask for a low energy effective action, for the massless degrees of freedom, you get a very, you get a systematic expansion in higher derivative terms. If you just truncate this expansion and you treat it as a fundamental theory, you get nonsense. But that's just the nature of effective theories. So in this setup, gravity is the effective low energy theory of string theory. There is no, in string theory, there is a string scale. Below the string scale, you have an effective theory, which is gravity. Above the string scale, you don't have particles. There is no graviton, there is no gravity. Above the string scale, geometry is not described by metric. That's why you can have things like T-duality. If geometry was really described by metric microscopically, then you couldn't have a T-duality.
And can we get some information about how geometry of space, or what is space-time at that scale?
So if you want to measure things at some short scale, you need your theory to have probes that can see such a small scale. If your theory does not have such probes, you might just think that not talking about the small scale makes no sense. Mm-hmm. So if you just use fundamental strings, they have intrinsic fluffiness. So it's really hard to probe scales that are smaller than the string scale. If you use D-branes, hypothetically, D-branes are much heavier. You could probe scales which go much higher than the string scale, and yet much lower than the Planck scale. Yeah, I don't. So, in some sense, the D-branes might be able to probe geometry at some smaller scale than string theory. But I'm not quite sure how to make a concrete statement along these lines. So, by the way, it's perhaps worth mentioning, there are theorems that, or pseudo-theorems or expectations, I don't know how to call them, that if you start from a quantum field theory at some energy scale, which has no graviton, you'll never get a graviton at a lower energy scale. So gravitons cannot emerge in quantum field theory as far as we know. I'm not sure it's a theorem, it's possible you can find loopholes, but I would say with relative confidence that you cannot start with relativistic quantum field theory at least and get a graviton at low energy. So if you want your theory of gravity to be an effective theory, effective low energy theory, it has to come from something which is not quantum field theory. String theory conjecturally provides such something. So if you have some UV theory which looks like string theory at some scale, at some lower scale you'll find the graviton. So in string theory, the metric, the graviton are not fundamental degrees of freedom. They're just emergent below a certain scale. I mean, you also saw when I told you what are the perturbative vacuum of string theory. They were just not labeled by space-times unless you insisted that you really want to talk only about sigma models as a worksheet theory, which I don't know why we do that. So the space of geometries explored by string theory are just not geometries, even perturbative. And then on top of that, you put the fact that you don't know what the non-perturbative definition is.
Well, but you start, sorry, but you start with the Gaiotto action that it's, well, you can say that you just imagine it, but that's like the embedding of a...
That's how you discover string theory. That's how you discover one perturbative vacuum of string theory.
But you're already there, when you put that action, you're already assuming that there's a 26-dimensional or a continuous space-time.
Yes, so when you start from that action, you get a geometric perturbative vacuum of string theory.
Mm-hmm. So
you didn't have to start from that action. Once you figure out the framework. And I mean, there is a huge risk of Lampos effect because we understand better some corners of string theory than other corners. We understand better supersymmetric setups than non-supersymmetric ones. We understand better sigma models than generic GVCFTs. And it's very dangerous to say, oh, this must be a generic feature of string theory just because it's a feature of the things you could solve more easily. If you decide to sort of abstract from the specific solvable examples you have at hand, it becomes hard to make you should abstract from the specific solvable examples that you have at hand.
In that direction, do we know how general the graviton is as an object that appears?
So I think it's automatic that whenever you have some something like a space-time in your string theory, you will have a gravity. Because the strings can naturally couple, because changing the metric of the space-time is a natural deformation of the theory, and every deformation of the theory wants to become a dynamical field. So if you want to list sort of general lessons from string theory, well, I think lesson 1 is there should be no continuous parameters in your theory. If your theory that is somehow resembles string theory, you should not have continuous parameters, only fields, only dynamical degrees of freedom, which might get fixed to specific values by dynamics. Another lesson is that that you don't see in string theory any evidence that unitarity and gravity would be incompatible. As long as you can speak about time and unitarity, then you don't see any obvious violations with the notion of unitarity. So the black holes you can study in string theory seem to be unitary objects, and so on. So there is a sort of a list of things that string theory suggests you don't have to do in order to get gravity that you might have thought you needed to do. In string theory, there doesn't seem to be a compelling need to discretize space-time in order to get gravity. Okay. But anyway, it's also saying that somehow it's probably misguided to hope that you're going to crack the problem of quantum gravity by trying to just look at the very small, very short distances. In the sense that if you think that the abundance of perturbative vacua is in the indication of what's really going on, then it suggests that there are a lot of dynamical situations which at low energy can give you a quantum field theory of gravity and some other degrees of freedom. And the specific number or type of degrees of freedom that you find is not particularly instructive. So just bootstrapping your theory of gravity out of collider data doesn't seem to be a good perspective. Unless in your collider you find something dramatic, breakdown of quantum field theory, or whatnot. So presumably, to understand quantum gravity, understanding global things is also quite important. There is some connection between the global structure of space-time and the microscopic physics that I think it's indicated by the ACFT, but I'm not sure what the sharp lesson to derive is.
I've heard that some people say that string theory is not compatible with a positive cosmological constant. Do you agree with that? Can you give us any?
No. Supersymmetry, unbroken supersymmetry is not compatible with a positive cosmological constant. So if all the models you can easily study have unbroken supersymmetry, then those models are incompatible with a positive cosmological constant. But its Lampos effect is not a...
What role does the cosmological constant play in string theory? Like, where does that requirement come from for superstrings?
In which sense do you call it a requirement?
I mean, you said that superstring theory needs a negative or non-positive cosmological constant, right?
No. I was talking about target space supersymmetry.
Okay. Oh, okay.
Target space supersymmetry is a property of some vacua, some perturbative vacuums of the string theory, once we control rest. is not a universal property.
And a supersymmetric target space cannot have positive cosmological constant?
That's right, unless supersymmetry is spontaneously broken.
Is there some intuitive way to see why that's the case?
Just so when you say some supersymmetry is not spontaneously broken, it means there is some global supersymmetry in this setup. Supersymmetry is squared translations, so naively this would just mean this time should be flat. There are ways to deform the supersymmetry algebra so that instead of anti-commuted translations, it anti-commuted to some other Killing vectors which form a different algebra. So you can get anti-supersymmetric in anti-de Sitter space, but it happens to be not possible in de Sitter space. But wait, there is a, when we talk about cosmological constant, of course, you get to the immediate big question: is the cosmological constant the result of microscopic physics, or is there some sort of IRUV relationship that helps setting it close to zero? Right? Because if you believe that the cosmological constant is really determined uniquely by some microscopic physics, by the dynamical choice of vacuum or something like that, then it's absolutely astonishing that it's so small. Right? And you need to start believing that somehow you're exploring an enormous space of possibilities, and you happen to be in a situation where it's large, so that it can be life and so on. Get into anthropic reasoning. I don't know if that's the correct way to think about it, but what string theory can tell you is that cosmological constant cannot be a constant in anything that resembles string theory, because it will be a continuous parameter. But ultimately, I don't think it's reasonable to make any claims about being able to derive some sharp predictions from string theory and low energy physics. Not until you find something, some non-perturbative description that is much more powerful than the one we have at the moment. Do you have any other questions?
You suggested that maybe ADS-CFT is the right place to look for a non-perturbative description.
I mean, the ADS-CFT definitely gives you a non-perturbative description of string theory in some negatively curved spacetime.
In what sense is that non-perturbative?
In the sense that there is an equal for super Mills is a quantum field theory. It's a fully defined object. And it just so happened that in the large N describes string theory in ADS5 times 5. And it describes it, not just perturbatively in the string coupling or in the Planck constant or whatever, it's just a full non-perturbative answer. Now, if you want to look at a spacetime that looks like ADS5 times S5 mod Z2, so ADS5 times RP5, you got to use a different gauge theory. That I find really annoying, because it means that some small change in the global structure of spacetimes forces me to use a completely different set of degrees of macroscopic degrees of freedom. That's really strange. So of course you can hope that there is a completely different non-perturbative description of string theory that applies to any space-time and specializes to these ones, and then for some duality happens to be the same as Nico for super mu. That's possible. Just don't have anything like that. So, and also, right, the SCFT, the way it's set up for the moment, it only applies to space-time with negative cosmological constant. You need to sort of put gravity in a box. So we don't know how to do cosmology in string theory. Part of the problem is just not being able to solve, just even write down and understand to solve two-dimensional conformal field theories. So our knowledge of two-dimensional conformal field theory is so limited that we cannot even write down a solvable, a theory which I can control and which will describe the motion of the string in the Sitter space. And plus, it's not even clear that perturbative string theory would think to try to do curvature. In the sense that if you do perturbative string theory, you're going to have a dilaton, which is going to control the strength of the coupling. And this dilaton will have to acquire some potential which fixes it to some value, because if you're not supersymmetric, generically scalar fields get potentials. And unless something conspires to this, so there are two possibilities. Either there is some conspiration that makes the dilaton happen to be very in a location which makes the theory itself weakly coupled, a weakly coupled string theory, or you have a bit of tension, right? If you're trying to use a weakly coupled description to build up a system where the coupling then spontaneously wants to become large. And why would you believe the original weakly coupled description? But right, computing the potential for the dilaton is hard, and it might not be completely perturbative. This potential might receive instanton corrections, for example, which are controlled by branes or even worse things. Not all of those are computed in complete perturbation theory.
First, when we are talking about the superstring, we put supersymmetry in the worldsheet.
Yes.
And then in the spectrum, we get these super partners also.
Yes.
But we don't have, that doesn't mean that we have supersymmetry in the target space, or does it?
So, so the supersymmetry on the worldsheet and the one on the target space are completely unrelated. There's just no relation between the two. Indeed, it's going to be really amusing. The geoso projection, the supersymmetry, was really a property of the theory before or the worldsheet theory before geoso projection. The geoso projection, among other things, throws away the supersymmetry generators of the worldsheet because there's spin 1/2, spin 3/2. And conversely, the supersymmetry in target space only emerges after the geoso projection, because the generator of supersymmetry is a Ramon-Ramon field. The gravitinos are an S-Ramon fields. So I'm not aware of any reason for which there should be a relation between the two. Also, so even in principle, you can imagine alternative descriptions of superstring theory which don't have worldsheet supersymmetry, like the range string. As you know, there could be different gauge fixing procedures of your worldsheet theory, which hide or destroy or removes worldsheet supersymmetry. Even we were very familiar with working with now string theory in a conformal gauge. That might not necessarily be the only thing you can do or the best thing you can do. For example, when Pedro and others, Shota and others, compute correlation functions, quantities in this ADS-CFT, ADS 5. They use constructions which don't seem related to conformal string theory and conformal gauge. They're string theory calculations. They're still computing amplitudes of string theory, but there doesn't seem to be any relation to a conformal gauge. Indeed, another thing I should say, so I mentioned, right, how in the bosonic string there is a one-to-one correspondence between the formations of the worldsheet theory and fields. In the superstring theory, things become a little bit more subtle. So the NS fields are really in one-to-one correspondence to the formations of the worldsheet theory, which preserve worldsheet supersymmetry. But the Ramon-Ramon fields are not, precisely because the supersymmetry generator is antiperiodic around the Ramon-Ramon fields. If you try to deform your action by the Ramon-Ramon fields, you will destroy the worldsheet supersymmetry. We have no idea what happens when you do that. It's a big gap in our understanding of perturbative string theory is that we cannot turn on Ramon fields, Ramon backgrounds. So there is sort of a list of foundational questions about perturbative string theory that are still open, don't need to be understood. So foundational question number one, understand better the space of two-dimensional conformal field theories, because otherwise your understanding of string theory is poor. Two, in superstring, find the formalism to discuss Ramon backgrounds. There are some attempts that seem to be going in the right direction, perhaps, but it's not clear. There is the pure spinor string, for example, seems to allow Ramon backgrounds, but has a baked-in target space supersymmetry, which might be problematic. But anyway, so this is another obvious, very basic question about string perturbation theory. Missing. So resolving this sort of foundational questions will expand a lot the range of applicability of string theory. For example, even in the ADS-CFT, in principle, you should be able to have a large N dual of something like QCD or pure Mills theory. Those are presumably perturbative string theories, but we have no idea how the worldsheet theory of the string theory would look like. And then, of course, there are all sorts of non-perturbative questions, like find non-perturbative definitions of string theory in spacetimes that don't look like ADS, and something. Or that some way to sort of produce, even in the case of holography, sort of some more systematic way to find which theories are holographic descriptions of string theory in some spacetime. By the way, another very amusing fact is which might be a Lamppost effect, that whenever you find a quantum field theory for which you can verify that it has an holographic dual, the holographic dual is either a string theory or M theory. This, though, so I don't know what the meaning of the statement. Because if you think about it, every consistent theory, every theory that has a low energy description involving gravity with negative cosmological constant will admit an holographic dual description. It's pretty much automatic. So you should be able, so for whatever is your favorite theory of gravity, if you can somehow cook up a vacuum with negative cosmological constant, you should be able to give an holographic dual as a conformal field theory. But at the moment, the conformal field theories you know how to control all end up giving you string theory or M theory. For some of them was kind of obvious because they came as they were produced first as a volume theory of branes. But for others, it's not the case. For example, this theory called ABGAM was not derived as a volume theory of branes, but it has an holographic dual which is M theory or string theory. So I would say third big open question. Try to understand better which conformal field theories can be holographic duals of theories of quantum gravity, and figure out why all the ones we know give you string theory. Can you find one that does not give you string theory? That would be an important question. Major accomplishment. Or can you convince yourself that somehow whatever you get is a string theory? That would also be quite interesting, of course. So there are big questions in conformal field theories in dimension bigger than 2. And these questions are starting to be addressed a little bit by techniques like the conformal bootstrap. So I would invite you, whatever theory of quantum gravity you like, I would invite you to try to see if you can find a holographic dual for that. That's the important step. Any other questions, topics?
I've heard some people express concerns about the rigor of the ADS-CFT correspondence. Like I've heard people saying that...
That's nonsense.
You don't agree with that?
Total nonsense.
Okay.
I don't know what more you could ask.
Okay.
I mean, the sort of checks that Pedro and Shota and others and many others have done of the ADS-CFT correspondence in many, many examples are astonishing. So at the tree level, in the string coupling constant, it's just manifest. Now people are starting to do loops. And they do match. But also, in general, the holographic principle is very, very robust. As I said, as long as you have a theory which, at large distances, looks like gravity, and it has a background or vacuum or whatever, which at large distances looks like negatively curved ADS, you get holography, no matter what's going on inside. In a sense, holography is completely, so holography is completely analogous to asking questions about the analytic structure of the S-matrix in flat space. So whenever you have a theory that looks like flat space, like Minkowski space-time, you expect to be able to talk about situations where you throw particles in. No matter what's going on at short distances, as long as the long distance theory is a quantum field theory, you can ask scattering questions. Right? The fact that you can talk about scattering is a purely infrared statement. In the infrared, I have these particles, and I can throw them at each other, and that's it. And then the S-matrix will have certain analytic properties. In ADS-CFT, it's completely analogous. As long as I have an asymptotic direction in space-time, which looks like negatively curved space-time, I can do the equivalent of scattering. I do some perturbations here and let them propagate in, some perturbations here and let them propagate in. And it just so happened that these analogous scattering matrices have the same axiomatic properties as correlation functions in a field theory. With the one-to-one correspondence between local operators in the field theory and the sort of things you can throw in. As long as one of the things you can throw in is a graviton, the field theory will have a stress tensor. So it will be a traditional quantum field theory. And it will be conformal. It will be a conformal field theory. It will be local conformal field theory. If there is no graviton, so if you're studying a quantum field theory in ADS space, you can still do that. It's actually a lot of fun. And then you just get a boundary theory which is conformal but not local, because it has no stress tensor. You can still study it, for example, with a conformal bootstrap. But yeah, so I think the SFT is extremely robust. And so it should transcend string theory. That's why I'm saying it should really be possible to find things whose orographic dual is not a string theory. Any other topics? Maybe I can say a few words about the branes and superstring theory. So, I mean, the worksheet definition is quite straightforward. So remember, so it's essentially, so if you remember, you wanted some boundary condition which satisfies this property, which in complex coordinates is something like t minus t bar, t equal to t bar at the boundary. And pretty much all you need to find a decent brane in superstring theory is that we have a similar condition for G bar. Okay. So there are some. So once you decide the boundary condition for the scalar fields like Neumann, Dirichlet, or whatnot, the boundary condition for the fermions follow pretty directly. And so you get things like psi is equal to psi bar or minus psi bar, depending on the boson being Neumann or Dirichlet. And so you can do easily the sort of things we did last time. You can study the theory on a cylinder with the boundary condition at the bottom, or study the theory on a strip. Now, then the specific details of the GSO projection will have funny consequences. For example, in type 2A, while in principle you can define a T0 brane, T1 brane, T2 brane, T3 brane, T4, and so on. When you look at the volume theory of these T branes, you find that some of them have open string tachyons. It's not a tragedy, but it just tells you that these T branes are unstable, they will decay. So they're really not stable objects in your theory. So this brings to lose the 1 branes, the 3 branes, and so on. On the other hand, the GSO projection introduces an extra choice, which is sort of the sign with which this T brane couples to Ramond-Ramond fields. And actually, yeah, this is an important point. These T branes couple, if you look at the cylinder with the boundary at the bottom, you find that these T branes couple to Ramond-Ramond fields, while the fundamental strings don't. So the T branes which survive in this list are precisely in correspondence to the Ramond-Ramond fields that we found. For example, type 2A had an F mu nu, and F mu nu is naturally coupled to a particle, and indeed there are the zero brane particles, and also the zero brane anti-zero branes. The D2 branes couple naturally to some F mu nu rho sigma, which is also there, and so on and so forth. So the type 2A brane, the type 2A theory has this collection in even dimensional branes. Well, they're odd dimensional in space-time, even in space. So, in a sense, the reason for which they're stable is precisely that they carry charges. The zero brane cannot just disappear into nothingness because it has its charge under the gauge field. Another important property of these T branes is that they have very nice couplings to the gravitinos, which imply that they preserve some supersymmetry. So I didn't count the supersymmetries for you, but if you look at carefully, you see that type 2A and type 2B have target space supersymmetry with a total of 32 supersymmetry charges. D branes preserve half of that. A nice flat D brane preserves half of that. The fact that they preserve some supersymmetry protects their properties. For example, the tension of mass of these D branes is proportional to their charge under their normal fields, and it's fixed. It does not receive quantum corrections. So that's a very useful tool to try to guess what happens to string theory, superstring theories when you make the coupling strong, because it gives you a list of objects whose properties you can control even when the coupling is strong, assuming that the theory with constant coupling makes sense. And that's how you find, for example, that type 2A at strong coupling becomes an 11-dimensional theory compactified on the SAR. That the zero branes become the Closure-Klein modes of the 11-dimensional graviton. The two branes and the strings combine into membranes in 11 dimensions, and so on. If you like to look at type 2B, instead you find the 1 branes, the 3 branes, and so on. And again, looking at the property of the D1 branes as you increase the coupling, makes you realize that they start behaving like fundamental strings. So the type 2B at strong coupling has a good chance to be the same as type 2B at weak coupling, with the strings replaced by the D1 branes, and vice versa. Another thing I can say about these D-branes is that the over-volume theory of these D-branes is a very supersymmetric version of Young's theory. So there is just a unique supersymmetric H theory with 16 supercharges, and that's the low energy over-volume theory of these D-branes. Another thing I can say is that if you put type 2A on a circle and make the circle small, you try to do T-duality like we did in boson strings, you land on type 2B on a large circle. So T-duality relates these two superstring theories. So even if you think to make some choice in defining these theories, you see they're actually related.
There's some Hodge dual-like operation that could take you between different.
Now, what happens is that, say, if you have a tree form here, you compactify it on a circle. Say that you can take the component of one of the labels goes along the circle that has 2 remaining indices. You can match it with the object 2 indices on the other side. On the other hand, the one that has all 3 indices not along the circle gets matched to the object with 4 indices on the other side and a leg along the circle. Anyway, I didn't discuss the details of T-duality as a bosonic string. It's a property. Another thing I should mention, so the superstrings were the theories which were 1,1 for sheaf supersymmetry. If you study theories with 1,0 for sheaf supersymmetry, you still get something sensible. You need to work harder. You have 10 bosons, then you add 10 fermions, but only on one side. Then you have a central charge which is 15 on one side and 10 on the other. You put your ghosts, but you only put super ghosts on this side. So you need to somehow, so the 16 is okay here, but the 10 should somehow become a 26. So you add 32 fermions on the right-hand side. You can play around with the JSON projection. Anyway, there is a variety of things you can do, but you get what are called heterotic strings. They have 16 supercharges instead of 32 in target space, in flat 10-dimensional space-time. They have no D-branes, but they have a lot more string modes, in a sense. But again, you can find non-perturbative dualities that end up relating superstrings and heterotic strings. For example, you can find a certain form manifold with a property that if you compactify type 2A on that form manifold, and you make the form manifold small, they start looking like heterotic strings on a Lie torus. So there are dualities that relate. There are manipulations that can relate all sorts of consistent theories that you can define, which have no atoms.
So how can you have no D-branes? Aren't they just like boundary conditions for open strings?
Yeah, but the problem is that when you have a theory which is not chiral, which has left movers which differ from the right movers, it becomes very hard to find a boundary condition. The boundary conditions typically match the left movers and the right movers. But at least nobody has been able to find boundary conditions for the heterotic worldsheet. It might be possible to do something which sort of mixes up the matter fields and the ghosts, but I'm not aware of any concrete construction. Yeah, so the question of do you make D-branes in a heterotic string is still kind of openish.
So does this just mean you can only have closed strings, or?
Yes, that's right. So you can, as far as we know, we can only make closed heterotic strings. That doesn't mean that there are no other objects in the theory. There are definitely all sorts of solitons which have tensions or masses for the 1 over G squared. But you lack this sort of D-branes which have tensions for the 1 over G squared. So before people discovered D-branes, heterotic strings were sort of preferred in trying to do phenomenological, semi-phenomenological models because they have, I mean, they have they have gauge fields, a lot of gauge fields inside. For example, the simplest heterotic strings have an E8 times E8 gauge field inside, or a SO16, a SO32. But then people found D-branes and realized it was also very easy to put gauge fields in type 2A strings. Let's see what other points. Do you have questions? Yes.
So how do you put gauge fields if not on D-branes?
Sorry?
How do you put gauge fields if not on D-branes?
Oh, just the closed strings here include gauge fields. Very naturally. A lot of the statements are in a sense already visible in the quantum field theory before it goes to string theory, in the sense that the matter content of theories which are chiral is very strongly constrained by anomaly cancellations. So essentially you can have violations to the homomorphism one loop violation of diffeomorphism variance target space, which only cancel if you have the correct collections of target space fields. The realization that the matter content of string theory precisely cancels anomalies was historically a very important step to make people believe that it was sensible to look at string theory, because they magically were producing non-anomalous series. And so here, for example, in order to cancel the anomalies that come from the Gavitinos, you need to have a certain number of gauge fields. Any other questions? Sorry.
So going away from branes,
Yes.
we know that the scale of the string theory, like the natural scale, is this string, the alpha string.
Mm-hmm.
So how do we know? We know that it's between that the top that it has to be less than the Planck scale.
Yes.
And bigger than the, I guess, than the energy that we can reach right now in the LHC, for example. But how do we know where it is exactly?
Well, you keep, in principle, you keep doing experiments at high energy until you find a breakdown of quantum field theory.
Well, but it could, well, from that that way, but how do we know that it's not the Planck scale or it's not above?
Well, the beautiful curse of renormalizable quantum field theories is that until you measure until you find something beyond, so the standard model is renormalizable, right? So it means that until you find some violation of the standard model, you cannot, it's very hard to know anything about what's going on at scales higher than the ones you can probe. There are some exceptions to this statement, but very limited.
And if we, for example, wanted to reproduce the standard model with string theory or some low energy string theory, how, if we just have this alpha string, how do we get the different coupling constants?
So they would have to be the result of a dynamical process, in the same way as the various coupling constants of the hadrons are computed from a smaller number of constants in the standard model. But first, the first question you should ask is, I mean, should I expect that there is the standard model and then quantum field theory breaks down? Or is there the standard model, some other quantum field theory, and then quantum field theory breaks down? If probably the second option, in the sense that because there is so much stuff in the universe which is not in the standard model, but is presumably still described by quantum field theory. Well, I don't know. It might be that dark matter cannot be described by quantum field theory, and that you need some. But I think that at the moment it's still reasonable to assume that there is some quantum field theory beyond the standard model which encompasses dark matter and other degrees of freedom which we're not aware of. And then once you write that down, you can ask yourself, okay, when I go even higher energy, is quantum field theory going to break down, or is there some other layer? Until you get a hint of a breakdown of quantum field theory, there is no point looking for the string scale. I mean, there is a big distance from the Planck scale to a 1 TeV. So much stuff that in principle could be happening. And the existence of dark matter suggests that something must be happening. On the other hand, the extreme degree of precision with which the LHC is testing the standard model suggests that whatever is beyond the standard model is quite higher energy. And of course, this gets quantum field theory's heads angled up in a loop, because it's hard to do quantum field theory without trusting naturalness, and then this becomes things absurd. So perhaps, yeah, I don't know what to say. In a sense, if you really trust naturalness, perhaps you should believe that the next thing that happens is that you break down quantum field theory. Because if you really just have quantum field theory, and quantum field theory sets in, let's say, a million tera TV from something else, it would seem completely absurd to have such a light Higgs. I don't know what to say. So there is definitely a tension with the idea that quantum field theory holds at very high energies and having a light Higgs. But I don't think anybody knows how to have a fundamental breakdown of quantum field theory at some energy just below the LHC that does not give you huge effects at LHC. So it's conceptually problematic. So if you don't want to believe in coincidences, there must be some mechanism that ties up UV and IR somehow. That manages to keep something like the mass of Higgs light, even as you go from some microscopic theory that is at very high scales. I cannot offer any such mechanism. Any other questions? Okay, maybe we can be done.
Okay, let's thanks Davide.